So in the previous video, I did the integral of capital F dr over the curve C, where C went from 1, 1 to 4, 1/4, by the curve y equals 1 over x. I first proved that the function was conservative, and then I used the fact that it was conservative to rewrite capital F as equal to del F, and then I applied the fundamental theorem of line integrals. Then I evaluated the line integral at the endpoints. That made it possible to solve. The problem with that, you could say, is that that's only two-dimensional. There's only x and y coordinates. So obviously you could have more complicated systems. So here, problem 15, you have these three components, right? You have first coordinate, which is yz, second coordinate, which is xz, and third coordinate, which is xy plus 2z. So you couldn't use the del p by del y equals del q del x. Well, you can use equation 29 on page, exercise 29 on page 1135. You could prove that for homework, and this will tell you how to check that a vector valued function in 3 dimensions is a conservative vector field. Now, it's going to involve 3 equations rather than 1, so it's a lot more difficult. But the problem tells us it's conservative, so we're going to assume that this function is in fact conservative. Well, how do we actually approach the problem now that we just assume that it's conservative? In the last example, we did assume it was conservative, but we also showed it. So how do I do this? Well, if it is conservative, then big F is equal to del little f. Well, del little f is f with respect to x, the derivative of f with respect to x, the derivative of f with respect to y, and f with respect to z. Well, that has to be equal to the components p, q, and r. So if I want to get the little f out of it, I have to integrate the first coordinate with respect to x, the second with respect to y, and the third with respect to z. So this tells me that f is going to equal the first component integrated with respect to x. So I get, there's no x here, so that's going to just give me x, y, and z. Now here's the thing. Remember last time, after I finish integrating, I have to pick up the other variables. So this time I'm going to pick up a function, and I'll call it psi. And psi is going to be a function of y and z, because I'm integrating with, to go back, I would take a derivative with respect to x, and that would kill off any y's and any z's. So this could be a very complicated function. It could be sine of y times the tangent of z plus z times y cubed, for example. If I take a derivative of that, the whole thing goes away. There's no x. plus 2,000 or whatever, plus some constants. Okay, similarly, if I take the integral of the second coordinate with respect to y, right? I pick up x, y, z plus some other function, but this is going to be of x and z, right? Since I integrated with respect to y. Finally, I do this again, right? But this time in the third coordinate, and I'm going to do it with respect to z. So I'm going to pick up x, y, z plus z squared plus a function of x and y. Now look, if I compare these 3 functions, I see this common theme, x, y, and z. Now here I have these 2 functions that are functions of y and z and x and z. Okay? Now, the thing left over here is z squared plus a function of x and y. So this has no x and y, but this has all x and y. These both have x and y, which means that y is located here and that x is located here. This z is here and this z is here. So really, this whole thing is just the phi and capital phi. Well, you might say, well, what's this? Well, that's just a constant. There is nothing else. We got nothing else. So to summarize all that mess, my function x, y, z is equal to x, y, z plus z squared plus a constant. Okay? So now let's use that to do a calculation. So I'm going to claim, well, okay, so this is equal to del f dr, because that's the potential function. And then we remember that this is equal to f r b minus f r a. Now, remember, I said that if a function is conservative, that it is path independent. So it doesn't really matter what path I use, since after all, it's going to be that, no matter what. So what is RB and RA? Well, this is A and this is B, so this will be f of 1, 0, negative 2 minus f of, got that backwards, say 4, 6, 3, and 1, 0, negative 2, and now I need to evaluate that. So this is going to be 4 times 6 times 3 plus 3 squared minus 1 times 0 times negative 2 plus negative 2 squared. Okay, so that's 0, and this is going to be, what, 24 times 3, which is 72, plus 9, minus 4, which is 72 plus 5, which is 77, and our answer is 77. And in the next video, we will start the next section, Green's theorem. See ya!